Good morning. Okay, good morning, and thank you for joining us. I'm Joanne Coons, your moderator, and I'm a renewable energy and sustainability enthusiast. I teach photovoltaic theory and design and installation and maintenance at Hudson Valley Community College. I'm a New York Geo member and participant and supporter of Solar Fest and their mission, and I highly recommend that you join both of these organizations as they are a wealth of knowledge. Thank you to the 1786 Meeting House to offer to host these the workshops called the Sharing the Best in Renewable Energy and Sustainability. We are kicking off this series with some knowledgeable and talented heating and cooling experts. Knowledge is power, and it can lead to a better life for our generation and for future generations. This will benefit our planet in the long run. And speaking about our planet, I want to give a special shout out across the big blue to our international attendees who are joining us today. And a big thank you to Mike Bailey, who organized and figured all the logistics to set up this series. I was looking forward to meeting you in person. In fact, I baked cookies for you all, but unfortunately, we can't meet in person. But as we've learned to be resilient in many areas of our life, I'm grateful to Zoom that we can still interact and howbeit different in a different way. So when I was younger, I heard that a building should be more like a tree, reaching down up to the sun with its branches and down to the earth with its roots for its energy. Heat energy is moved to the benefit of the tree, and it's not burned and one time wasted. Our buildings would be energy producers, not consumers. Now, this vision has really stuck with me throughout my life, which is why what our presenters have to share is so spot on to our future success in managing our energy needs in our building. Okay, I'm going to briefly introduce each of our presenters now. During the presentation, if you'd like to put questions in the chat, we will answer them in the last half hour. If you want to share this video or this presentation or view it again, our Solar Fest guru, Mike Bailey, will be posting it on our website soon. So first off is Matthew Damaris. Matt is the founder of Energy Catalyst, a growing heat pump manufacturer who is launching a line of geothermal heat pump conversion kits in early 2022. Geared specifically towards replacing a boiler with geothermal, Matt has 8 years of professional engineering experience, including working with clean energy performance contracts, HVAC upgrades, industrial and cooling tower heat recovery, and geothermal technologies. Matt has been involved in projects in 6 different countries and has 3 patent pendings in heat pump technology. And by the way, Matt grew up in Bear, Vermont. Next is Kevin Ravik, and Kevin is a driller and geothermal installer. He's on the New York Geo board. Kevin is president of Barney Moravik Incorporated, a company that has developed well over 800 geothermal installations and drilled more than 1.5 million feet of closed geo-exchange loops. In 2016, Ravik purchased Van He Heating and has overseen the development of the company to be a leading installer in both ground source heat pumps and cold climate air source heat pumps. Van He has installed over 4,000 ground source heat pump systems since 1979. More recently, Kevin helped create the Ground Up Geothermal Alliance in Western New York, an organization that created a standardized methodology of ground source heat pump installations, a custom loop system along with 100% domestic hot water and water furnace variable capacity 7 series. And lastly, but not least, is Robert Jensen. Robert is a mechanical engineer and a physicist. Yes, it's all about science, who started his career as an engineer for a major HDPE pipe manufacturer, where he developed many new products, including one of the earliest factory-installed geothermal U-bend systems. He was also awarded a patent for a novel heat exchanger before moving on to a more entrepreneurial endeavor. Over the next 1.5 decades, Robert built several companies related to manufacturing and engineering, but always retained a passion for geothermal heat pump industry. In early 2010, Robert founded Greenability with the intent of developing the first economically beneficial, high-efficiency ground heat exchanger. The Twister heat exchanger has resulted from this effort and now is saving thousands of dollars in geothermal installations throughout the country. Publications include related articles in Worldwide Drilling Magazine, National Driller Magazine, Wall Street Journal, and more. And Robert has also been a speaker at several geo-related events such as ISHPA Annual Conference, New York Geo, and Pennsylvania Water Well Association. Okay, so we're going to start with Matthew, who's going to give us a short overview of what heat pumps are all about, and then explain what his specific technology does. So Matthew, thanks.
Yeah, thank you, Joanne, and thanks to Mike for setting this up. So hello, everyone. I kind of want to help kick off this whole kind of workshop with probably the answer that I give to people who ask me the most common question that I get, which is, if you have 50-degree hot water in the ground, 50 degrees, how do you make 120 degrees in your house? It just doesn't make sense to most people. And it does take a little bit of time to kind of understand the technology. And so this is the answer that I give. So I'm going to kind of break it down for you. So the first thing to think about when you think about geothermal heating systems is think about it as a device that moves heat from the ground into your home at higher temperatures, right? You don't think of it as creating heat. If you're used to an oil-fired boiler or propane boiler, that's creating heat because you're burning a fossil fuel. What a heat pump really does is it moves heat from one place to another, and they don't need to be at the same temperatures. So a classic example of this that you already have in your home is a refrigerator. So a refrigerator, it moves heat from inside the box, basically your refrigerator box, to the outside. Usually it blows it either underneath or out the back or something like that. So you already have a heat pump in your home. And it's already that even a refrigerator is over 100% efficient. So the technology that we're talking about, we can see efficiencies of between 300 to 500% efficient. And what we mean by that is that we're moving, let's say 500% efficient as an example. That means we're moving 4 units of energy and we're putting 1 unit of energy in, and the result is we get 5 units of energy on the other side at the cost of only 1, right? So when people talk about, super high efficiencies, again, one of the core ideas I want to impress upon everyone is that it's not because we're creating energy, it's because we're moving it. So going back to that core question, how do you get 120 degrees with 50-degree water from the ground? So the way I try to explain this is I have a glass of water here with me. And I want you to imagine that this inside here, we just have a fixed amount of liquid, right? And we have a completely solid metal container. So that can't expand, can't bulge, it's completely solid steel. So if I was to take this water and I was to reduce the pressure inside the vessel, inside this enclosed space, what do you think would happen to the boiling point of the liquid? Now, I don't know if anyone's brave enough to shout out an answer, but does anyone want to take a guess real quick? Joanne?
Oh, we're going to increase the pressure. You're going to cause the molecules to move faster and reduce the boiling point.
So correct. So if you reduce the pressure, and we sort of instinctively know this, right? If you've ever boiled pasta at high altitudes, you have to, yeah, there you go, Bob. Perfect. So if you reduce the pressure, then the boiling point is going to drop. You're going to boil this at a lower pressure. And so it is actually entirely within the laws of physics that if I got this pressure inside the vessel low enough, I could boil the water just with the temperature of my hand right here. That's essentially how a heat pump absorbs heat from the ground. So when you want to think of the moving of heat from one place to another, what I sort of tried to describe is that you're boiling refrigerant on one side, right? And that's what you can see here. We reduce this pressure all the way down to the point that it boils. And if we have an air source, or if we have a ground loop that may be operating cooler, we just keep reducing that pressure down until it boils. That's one of the big core ideas. So as this thing, we're boiling off this vapor, right? And then it gets to the compressor. And now the compressor, what it's seeing is a solid volume of vapor. And all the compressor can do, a lot of times people give the compressor a lot of credit, but think of the compressor basically as a pump. It's just moving it from one side to the next, and it's moving it from low pressure to high pressure, right? Not that different than an air compressor. And now when you get to that high pressure, what's going to happen is you've now raised the pressure above what the old boiling point was. And so now naturally, because we know if you lower the pressure, then you're going to reduce the boiling point. Well, now if you raise the pressure, you're going to raise the boiling point. And so what'll happen is the boiling point is raised, but now we put, and I do have a quick visual here that I'd like to share. So this is the point that I'll bring this out. Can everyone see this? Joanne, just give me a quick thumbs up.
Yep, you're good.
So now that we've raised the pressure on the other side, now we can condense and absorb that heat on the other side, on the condenser side right here, by raising that pressure up. And so this is essentially, if you want to think about it, what a heat pump does constantly is it's constantly boiling a refrigerant, a fluid on one side, and then condensing it on the other side. And so all of that heat, we instinctively know when you boil water, it takes a lot of energy to boil water. Well, refrigerant is the same thing. So it takes a lot of energy to boil a refrigerant, and then that refrigerant, as it condenses, it releases that same amount, roughly the same amount of energy on the other side. So that's just kind of a really quick overview. And I think this diagram, I took this from an old colleague of mine, but it's a decent explanation and a really kind of high level overview of how this technology works, where, if we can draw heat from the ground here, we, showing a different range, 55, 40 degrees, 20 degrees. Generally speaking, the more efficient, you're going to be more efficient if you have higher temperature fluid coming in. And then you're also going to be more efficient if you don't have to supply as high of temperature, right? So you can kind of think of these, the temperature at which you're absorbing heat and the temperature at which you're discharging heat. It's very important that you get those temperatures as close together as possible. And that actually brings me to the product that that my company manufactures. So we are a geothermal heat pump manufacturer based in Albany, New York. And what we've devised is a device that it's really designed to be the perfect retrofit for a home that has an existing boiler. So if you have an oil-fired boiler, a propane boiler, and you have baseboards or radiators throughout your home, it's typically very difficult to release that heat at low temperatures, right? We don't want to supply 140, 150 degree hot water, because now you have a really large differential, and that's going to lower your efficiency. So what the device that the heat pump that we manufacture does is it basically brings, even though we can supply 120 degree water, we drop down the compression ratio. It kind of gets into some heavy thermodynamics, but we reduce the impact of that significantly by also blowing a small amount of cool air across the refrigerant at the end. And so this dramatically increases our efficiency. We see efficiencies that are at least 50% better, if not 75% better than a regular high temperature water to water unit. So that's kind of a really brief explanation of both how the refrigeration cycle works, how we can get 50 degrees up to 120 degrees, and then just a little bit about, kind of what we're doing. And if anybody here is interested, our company is called Energy Catalyst. You can find us at energycatalyst.org. So I think I'll leave it at that, Joanne. And if anyone has any questions, feel free to enter them in the chat afterwards. Thank you.
Okay. I was thinking about putting these websites up, and I didn't do that as you gentlemen were speaking. So let me see if I can get that. I'm not sure this is going to work, but we'll give it a try. That. All right, so this is Matthew's website, Energy Catalyst, so you can get to know him and see where his how to reach him, I guess, is also another possibility, is another reason to check this out. All right, thank you. Remember to put your questions in the chat. The next speaker is going to be Kevin Ravik, because he's the well driller, and we need to start with a well, and this is his website. You can contact him there. It's easy to get to, ravikgeothermal.com. And okay, Kevin, you ready? Oh, unmute, I think. I can't hear you.
You can't hear me? Can you hear me now?
It's a little bit fuzzy, but
Is it fuzzy for anybody else?
No, that's good. That's good.
Okay. Sometimes I am a fuzzy person. I've never been accused of being warm and fuzzy, but I can be fuzzy. So, yep, thank you for having me today. It's always fun to be able to talk about what it is that we do on a little bit broader scale than most of the one-on-one conversations we have with homeowners. I am Kevin Ravik, president of both Barney Ravik Incorporated and Van He Heating, New York Geo board member, as Joanne mentioned. And I do just about everything that's involved from the residential side, design, loop installation, the drilling aspect, horizontal loops, air source heat pumps. But a big focus of ours has always been the ground loop piece. My family's business was started in 1934 as a water well company in the Finger Lakes region of what we call upstate New York. And we started drilling geothermal bores in about 2007. Started getting some popularity. And from that point on, it's become a core piece of what we do. A lot of new construction projects. If somebody's building a house, you almost always have to have water first. So that's always been our company's core focus. And in the last 12 or 13 years, it's also become, well, if we're there to drill you a well, that provides you with water, we can also provide you with the source to heat and cool your home for the next 300-400 years. It's a really, really easy process. And it's always an interesting thing the first time somebody sees a drilling rig do a geothermal project. It's messy, it's loud, it's involved, it's not that simple. We make it look simple. But when it's done, it's the single greatest piece of technology that somebody can put into their house. And not every home or every piece of property is ready for geothermal in this day and age. Certain tight lots or geological conditions can exclude certain sites, but most sites we're able to put a geothermal system in. And if we can't, we can offer an air source solution. And as Matt said, you go through that whole process of explaining the refrigeration cycle. I've gotten to the point where I just say it's magic. It's magic that works reliably. I can go into the explanations of it, but my simple bit of terminology for it is we take a huge amount of energy in the ground, whether it's a horizontal loop or vertical loop, and then the heat pump can concentrate it and it moves it from one place to another. We can do the same thing in your home in the air conditioning mode. We just take all of the heat, excess heat that's in the home, concentrate it in a heat pump, and then put it in the ground. I'm reading the chat on the side. That is, I like that. It is indistinguishable from magic, I think. It's a weird thing in upstate New York. I've been at this long enough that early on, we used to have to explain the technology and how it works and justify it. And the last 5 or 6 years, almost everybody that we talk to knows somebody that has geothermal. They're putting geothermal into their second house. They're very comfortable with the heat pump technology in general. And there's a major push to get away from fossil fuels. And the programs such as this and what NYSERDA has done in New York State, and now the Clean Heat and Cool programs have done a really good job of showing people how reliable the technology is and the wide range of applications that we can do this in. Our standardized process that we started back in about 2017, we went official in about 2018 with it, of coupling 100% domestic hot water with a variable capacity 7 series and a standardized bore, really has made the process of installing these systems much easier, much more adaptable from a home to home situation, and very, very comfortable. One of the key components to any bit of technology and gaining the trust of the public has been the ability to monitor performance. So it basically justifies our designs and holds the contractor's feet to the fire, which is unique, I think, to the geothermal side of the business. We are able to monitor and show that data in live time. We can do diagnostics remotely. I can adjust efficiencies, reduce pump watts, blower watts. And it's just really been a phenomenal way of putting systems into homes. The drilling side is still the #1 bottleneck in the industry. I'll say that. There's very few rigs around that do this regularly in New York State. Recent survey that we've worked our way through, there's about 55 drilling companies that are capable of getting a bore to 500 feet. There's about 30 companies in New York State that are capable of looping and grouting that borehole. And there's about 13 of them that are capable of going drill, loop, grout, and tie into the building, which is one of the things that is the industry grows. There's a lot of HVAC contractors that have experience with heat pumps or connecting to systems. Getting it set up easier for new contractors to not have to play in the dirt, so to speak. That's one of the big pushes that our industry is working on right now, trying to get more drilling rigs, get more people interested in it. But it's a lot of fun. We enjoy it. It's not like solar, unfortunately. There's nothing there after we're done that says, yep, they have a geothermal system. It's all buried beneath your feet, and it works quietly inside your basement for a long, long time. So I think that's about it. I think we're going to Robert next, right?
Right. Thank you. That was great, Kevin. And just FYI, I'm enjoying the nice warmth heat of my geothermal system as we speak. We've had it for 11 years now, and served us very, very well.
That's one of the most disappointing things about my setup is I've done all those different heat pump systems. Every building I own, every family member of mine has a geothermal system. And I live in Fairport, New York, which is a municipal electric setup. And we hit a massive pocket of natural gas, one of those geological conditions. So I have an air source heat pump in my house. I couldn't put geo in, and there's very few sites that I can say that about.
Interesting. Okay, so Rob, would you like to explain the twister and your technology and how it fits into the mix here? Thanks. Hang on, Rob, unmute, please.
Okay, how's that now? We good? Yeah.
You're good.
Okay. I went ahead and prepared a few slides here, so I'm going to try to bring them up on the screen, right? If I can figure that out. Is that showing up? Oh, no, that's not showing up, right? Share. How about that? Is that there now? Okay. Very good. Let me just go like this. Okay. So this is just the introduction. Yes, I'm Rob Jensen and the founder of Green Ability. And we manufacture this heat exchanger right here, which is, the ground loop, the portion that goes in the ground in a vertical loop. This is a novel type concept. I'll talk very little about what the standard product that is used out there today, but we'll explain a little bit about this product here. So just as an agenda, I'm going to just talk about the three types of connections real quick that we have with the ground, but I'm going to focus on the vertical bore and then talk about the twister, the description, the benefits, how it works, and a short video so you can see it and talk about a few case studies of it. So first of all, Matt did a wonderful job of explaining, how a heat pump works. The ground loop is a connection to the earth that then is where we pick up that heat and drop the heat, which is obviously an important component of geothermal. And there's three main types. There's the horizontal system, there's the vertical system, and a pond loop that we use. And horizontal is basically we lay out trenches and we put pipe in the trenches and cover it up again, and you get an earth connection that way. And a pond loop is effectively also an earth connection. It's just that you're getting your connection through the water. Water is a very, it surrounds your pipe well, so you get good heat exchange from water as well. And then lastly, and I think the most commonly used system across the country is the vertical bore, which is where we drill this hole in the ground and we put pipe in it. So we'll talk mostly about the vertical, and I'll go on here. So we have several steps that we got to take. First, we got to drill a hole. That's that big drill rig there that's in the picture. I realize now that, well, that's never mind. Then we insert the pipe, and you got typically that picture that you see down there. I guess, can you see my cursor? Probably. It's a typical two-pipe system where water flows in and out of the borehole. It has this outer circle represents a borehole wall, and then in between the pipes is grout, which is fed into the borehole through this third pipe, which is a tremuline, we call it, and that pumps grout, which is a clay or cement type material with some thermal enhancement in it, like sand or graphite, to help connect the pipe to the ground so that you get proper heat transfer. Typically, around the country, residentially, we install about 150 feet of bore per ton of heat pump capacity to achieve fluid temperatures that are acceptable to the heat pump performance. Loops that are too short, will cause temperatures to deviate outside of that, high heat pump performance range or operating range. And loops that are too long waste money because drilling is expensive. And as we mentioned earlier, that there's only limited capacity, so of drilling. So to drill too much is not really good. To improve the performance of a borehole, we can reduce. We have a certain we can improve in performance, reduce drilling, or reduce costs. We can employ certain things such as high conductivity grout, bigger diameter pipe, and then novel pipe concepts. And obviously novel pipe concepts is what I'm here to talk about, which is the twister. And our product is, instead of that other picture that I showed you, we have, where there was 2 pipes, we have 8 pipes altogether, 4 loops that are centered around a center grout tremie pipe conduit, which does a couple of things, which I'll talk about in a minute. But these are, each loop has a separate U-bend at the bottom. It's capped off for protection for during insertion, and it looks something like that. And I don't know if you guys can actually see me, but here's a piece of the pipe, give you an idea of sort of the size and feel of it. So the benefits of the twister is that you get more efficient heat exchange. There's a fast installation. I have videos to show about 500 foot this pipe going in the ground in 4 minutes. There's a superior grouting process because it eliminates some of the grouting snafus that can happen when you're inserting that tremuline through the center pipe instead of going through the outside of the pipe with the conventional methods, where you can run into fractures and the like. And collapses of the hole. We have a constant open center pipe to get that tremuline down. And the result is about a third less drilling. We do about 100 feet per ton versus 150 feet per ton to get sort of the same performance. It gives us a 20% reduction in loop field cost, and it can improve performance as well based on design such as lowering pumping costs of the system and improved temperatures as well. And how it works is that we have a value called the borehole thermal resistance, which is just a measure of the effort basically for heat to move from the pipes to the ground or from the ground to the pipe. It's the resistance to that movement of heat is a borehole thermal resistance value. And with a pipe concept such as ours here, the twister, we have reduced that number by as much as 80% compared to the standard borehole thermal borehole technology. And we do this by maximizing heat transfer surface area. Obviously, there's a lot more surface area to transfer heat in this concept than here. The pipes are nearer the borehole wall, which reduces that resistance to heat transfer. And then better flow characteristics, meaning that we get good heat transfer via the fluid flow regime at a much wider range of flow rates than a standard product. And that's because of the twisting of the pipe. Again, the pipe is twisted around, it causes this turbulence type flow. So the bottom line is the result is a reduced drilling requirements and enhanced performance, as I mentioned earlier. This is a little video of an installation, just a short clip here. I don't know if that shows up nicely or not, but that should give you an idea of how this goes in. It goes in very quickly with pretty much the same type of equipment that's used today for installation processes. So, and it's made of the same material that that is being used, high density polyethylene. So it's fairly standard process, and I won't. But yeah, that's it. There, I won't bother you with any more of that. But so we started back in 2012 and installed a number of case studies to prove the performance of this system. In this particular case here was a 3,500 square foot remodel. It's a 7-ton heating load. We installed about 85 feet per ton for this particular project, which is very little pipe compared to what we standard would do. This is also a little further south than most of New York. It's in northern New Jersey. So that has some impact on loop length, and we could go a little shorter here. And so I haven't included all of the data and everything here because I think it's too much, but we monitored loop temperatures and BTU exchange, and we placed the system into operation. And back in 2012, 2013, it was one of the worst winters that we had around here in a long time, and the system performed as expected throughout that. And we demonstrated a 20% reduction in loop costs while maintaining the performance. We did subsequently a number of different projects to do the same sort of verification. Most of these, I think, were in New Jersey, but ranging in size from 30 tons down to 3 tons. These were done in 2012, 2013. Again, these were the earlier projects, but we demonstrated savings. I got my screen in front of me, but $13,000 down to $1,500 depending on the size of the system. Since this time, we've installed over 1,000 projects from California to Wyoming to New York, obviously, pretty much all over the country. So that's about it. That's my part. I think there's one more slide that says thank you. All right. So I'll stop sharing here. Okay. So everybody's on mute except for me now. You're on mute, Joanne. Am I supposed to do something?
It's that pesky mute function.
Yeah.
Rob, there was a couple of questions that came up in the chat.
Oh, okay. I'll look at
In a
them.
minute. Why don't you go ahead and address some of those?
Yeah. Already has a water borehole. How easy is it to accommodate geothermal pipe system? Typically, water wells to drill to 6-inch diameter. I've been involved in a number of retrofits of existing boreholes to take it from a water well to a geothermal well. But Derek, Kevin, you might be able to answer more of what is involved in actually converting it. Do you have to remove anything from it or anything like that?
A lot of it really depends on the age of the construction of the bore. How deep is it and how it was drilled? Because if it was drilled recently with a modern rotary rig and you have a fairly standard bore depth down to the bottom, you can potentially use that as a portion of the bore. What gets tricky is you almost always have to investigate what that water well is drawing from. Is it from rock, or is it a gravel well? Is it a sand well with a screen? Because if it's in gravel and it's not seated into bedrock, it's really not a usable bore. You can't continue to take that casing down to top of rock. That's one of the big things that we deal with drilling a geothermal well. Is the closer to surface bedrock is, the easier it is to actually drill a geothermal project. Sand and gravels and mud drilling and sonic technology and all that other stuff is, it presents challenges. And I'm just looking through there. Granite is not really an obstacle. I mean, we can drill through just about anything. There are some types of rock that are worse than others. And granite is hard, there's no doubt, but all that does is extends the length of the drilling process. We can in some soft shales, depending on the drilling technology that we do, we've done upwards of 1,500 feet, 3 different 500-foot bores in a single day. In some limestones, depending on what's in it, you can do around 100 feet an hour. 80 to 120 feet an hour is fairly standard in limestones. Granite, you might be in that 40 to 60 feet an hour range. So it's just a product of time. Sometimes we will throw an additional bit charge in there. We buy a special hammer bit to deal with really hard rock. But there's really not much of a situation in bedrock that we can't drill through. I do not operate in Eastern Massachusetts. I'm Western New York for the most part. We've drilled in the Hudson Valley about 4 years ago. And we're so busy and where we are that, it's tough to expand, obviously. There are, I don't know if you want me to keep going through these questions, Matt or Joanne. Okay. Reputable company. I would say that's a lot easier to do today than it probably was 10 or 15 years ago. Usually 15 years ago, reputation was based on word of mouth and local references. Being able to talk to a homeowner that has had a system installed and in being able to view some of the monitoring data, modern situations in New York State, the programs like the NYSERDA and the Clean Heat, Clean Cool program that the utilities are running, you have to be a vetted contractor. There's a QA QC process that ensures that what we're doing is correct for the home, that the sizing is correct. Variable speed technology has taken a lot of guesswork out of things. A manual J is required in every home. There's a little bit of good in, good out, garbage in, garbage out with some manual J's. So definitely want to do a good energy analysis on the house, get an audit if need be. You can do a true up based on fuel consumption in a home. And all these different things point you to the size and design of the HVAC system. Their questions are coming quick. Typical range of savings for heat pumps versus oil or gas. Gas we'll talk about in a second. Oil and propane, we typically see about a 70 to 80% savings over fuel oil or in propane. A standard 4-ton system with an 80 to 90 million BTU annual load, you'll see an annual operating cost with what we put in between $550 and $700 a year annually for heating, cooling, and domestic hot water. As the load goes up, obviously the cost goes up, but back to what Matt said, the COP, that one energy of work to get the free stuff out of the ground, you're not getting penalized near as much as the load goes up. 2,500 to 3,000 square foot home with a full 5-ton system, family of 4, relatively tight envelope, you can range between $800 and $1,000 a year versus $3,000 to $4,000 in fuel oil or propane costs. I think that this year is going to be interesting because we're heading back to what we saw in 2014 and 15. The first time that anybody really, polar vortex became a word that everybody knew. And that's when fuel oil and propane prices spiked. Unbeknownst to anybody, now they're predicting it. So against natural gas, a geothermal system will probably save you 30%, give or take. Air source systems, all across the board, you're going to increase your operating cost by 25 to 30%. It depends on the winter that you have. If you're a little bit farther south, down by Rob, where the temperatures don't dip quite as bad as we see up in, upstate New York or some of the Hudson Valley mountain regions that border on Mass, you can get some really cold temperatures, and ground source kind of insulates you from that. No, Bob, that is not accurate. You can put a geothermal system into anything.
Actually, do you mind if I answer that one, Kevin?
You got it. Yep.
So Bob, I see this, you asked the question, and just for everyone's benefit, I'll basically repeat it here. He's been told that heat pump could not work in his house because it relies on forced hot water. He's got an oil boiler and baseboards, and a heat pump won't get the temperature high enough. Now, what people have told you is there's a good degree of truth in that. So when you go from an oil boiler, which is operating at about 180 degrees, maybe 160, to a heat pump, which has a max temperature of about 120 degrees, you're going to lose about 75% of the heating capacity of your building. That's going to happen. What people don't always realize, though, is that your baseboards are almost never running all the time. In the data, so I got my start by taking a lot of data analysis for multiple winters on homes that had baseboards, and even homes that used a lot of heat, like old farmhouses from the 1800s. even they typically were only using their baseboards about 30 to 40% of the time. So you can compensate for it simply by running your heat longer, which actually is more comfortable anyway. You would probably rather have nice, stable, consistent heat that's at a relatively low, temperature versus this kind of up and down, right? So, and that's exactly the other thing that our heat pump does is it ensures that a contractor such as Kevin, for instance, doesn't need to worry. He doesn't need to go in and do the analysis to figure out, okay, do we have enough thermal loading? Probably, Kevin, the way you would have traditionally done this, right, is you would have put in a hydronic air handler or some type of backup system in the house that blows hot air as a supplement. Is that probably traditionally the way you would have done it, or some people add,
There's a couple ways. I mean, the heat pump technology is advanced enough that we can see 100. They'll say 150. I don't like it.
I don't buy that.
Yep.
40.
I've seen it. You can get it. 140. We prefer that 130 range. 135 is the upper end. So we can use some of the baseboards, but you're right. In almost every situation, we're looking to add some kind of fan coil system, either a ducted one or a hydronic fan coil that looks like a mini split. And usually that conversation is more based on they also want cooling added into the building.
Right.
I've seen people replace the baseboards with aluminum core, like Heating Edge 2 products that you can operate at lower temperatures. But that's pretty standard for how we do it.
Okay. Yeah. And so the way that so my company is really hyper specialized in solving this one core problem, Bob. And what we build is a heat pump that it's going to fill all of your, existing baseboards with about 120 degree hot water. But then whenever your building needs more heat, or let's say whenever the heat pump is capable of producing more heat than your building is capable of releasing, the difference is automatically released as hot air. So we basically took what is traditionally done as multiple pieces, where you have a separate backup heating system and a heat pump, and we put them together into one unit. And this is actually proven to be quite a bit more efficient way of operating as well, and it's faster to install. So, and I guess if I can just add one other little bit of a plug for ourselves, we are offering this winter to anyone who is interested, we are offering a measurement of your home's thermal capacity. So we will come to your home and we'll take a measurement of the thermal capacity of your baseboards, radiators, whatever you guys have. And based on that, I think Joanne's sharing something, but based on, there you go. There's our flyer. Based on that results, then we can help determine, we'll know exactly what your building needs in the dead of winter at every temperature, and then we'll also know what the capacity is. So we can basically align your building load with the thermal capacity of your building. So it's a pretty clever way of doing it. We only kind of figured it out after playing around in the industry for a number of different years, but it's kind of a good way of doing it. So if anyone's interested in taking a look at that, I think Joanne will maybe share the flyer. Yeah, okay. So
I've seen it come up a couple times. People are curious about cost to install a standard system. Standard is an interesting word, but I can say that in Western New York, with how we do things, if somebody has a forced air system, and if it needs to be a vertical closed loop, with all the incentives that exist in New York State, we're primarily NYSEG and our NYSEG, RG&E, and National Grid service territory. So they're on the lower end of the spectrum with some of the rebates that exist. You're usually in the mid 20s after all the incentives to do a turnkey system. Standardized bore, variable speed hot water or variable speed forced air system, and then hot water capacity in some shape or form. Now that's premium product. That's the Water Furnace 7 series. It's the best piece of equipment on the market for forced air heating and cooling. But there are ways to lower that cost. You can go with two-stage technology. I'm not a fan of it. It puts a little bit more emphasis on being correct when you're looking at the cooling load of the home and the borehole design and how it performs as you switch from heating to cooling. And that in some cases, unless the first stage and second stage align correctly, you may have to rely on a little bit of auxiliary boost on the coldest 100 hours of the year. So it's not a big deal. It might cost you an extra $75 a year to compensate for that. But you know, if you get over into the eastern part of the state, it shouldn't be much different than that. The rebates are a little bit better than what we see over here, but typically in that mid-20s range for, you know, what we call a swap out. We don't have to do a major duct modification or anything of that nature. You know, we're a turnkey company, so we build our duct systems in-house. So we're able to be a little bit more flexible. We don't just specialize in bolting in a heat pump or just drilling a ground loop. Drilling is a little bit more expensive on the eastern side of the state than it is on the western side. Although that's probably true everywhere with the cost of casing and fuels going through the roof in the last 12 months or so. A smaller home, believe it or not, doesn't change the out-of-pocket cost all that much. There's the first cost of mobilizing the equipment, drilling a ground loop, purchasing a say a 3-ton heat pump. It's not a huge difference in cost to go from a 3-ton to a 5-ton. And the flip side to that as well is the rebate is smaller on a 3-ton piece of equipment. So you're probably still going to be in that mid-20 range. It could be slightly higher than a standard 5-ton system. If you happen to be in Con Ed territory, it's definitely even it's even cheaper than that from a rebate perspective. I don't know if there's anything else in there.
I just wanted to mention that I believe geothermal heat is really solar energy. And I wanted to throw that out there since this is Solar Fest, because the sun has been heating the earth for 4.3 billion years. And that residual heat of the surface is what we're pulling and using to heat your homes. So it's a way to look at things maybe a little differently, but we're bringing it back a little bit further down the line. You know, I just see that it's pertinent to our discussion. Okay, we had another question here that was, I did have a couple drilling questions too. And also I had a question for Rob about that twister. So let's see, Deborah says, is there anyone doing geothermal in southern Vermont? I believe there is. And
There are.
I think that we're going to be posting some resources for you on our website, so that if you contact that or you go there, I think that'll help direct you. And I feel bad that we didn't have anybody from Air Source to kind of give that side of the fence idea. You know, it's also a heat pump, but using air versus the ground, because there's air down to negative 272 Kelvin. There's still energy in our air that we can pull from. And I know that heat pumps, Air Source heat pumps, have been thought of as being not possible to use in northern climates, but there's newer technologies that we have to, it's kind of like the LED light bulb, you know, from the CFL. It's improved to the point that we have cold climate heat pumps now. By the way, we've never used our auxiliary heat in our heat pump. We have very, very rarely gone to stage 2 and never had to dip into our auxiliary. So that's just our experience. That picture in the twister, Rob, when it was pulling down the twister into the borehole.
Yeah.
How does it go so fast? Is there a pulley, or I'm just kind of curious?
In that
Is it
particular
gravity?
borehole, it was probably, I mean, if there's no water in the borehole, it goes in very quickly.
That was amazing.
It
And if
scares you.
there's a lot of water, then it takes more time, you know, and a counterweight then is used to make it go in a little faster
Okay.
to help
All right.
pull it down.
You know, if anybody
Do
ever
you
gets a
fill
chance,
those before they go down, Rob? Do you fill them with water?
If there's no water in the borehole, no, we don't.
No,
But
no. I get that.
Yeah. But otherwise, yeah, we typically fill it with water. You have to, otherwise it's too buoyant. It won't go down.
No.
So, yeah.
if anybody gets an opportunity to watch a drilling, it's really amazing. It's really cool. And these are all good, really live experiences. I know we're talking about stuff here, but seeing it is really much better. So,
I
that
was
might be a-
hoping to have the video for this, but we did do a live capture of an entire process.
well, you can send it and we'll post it on our website.
Yep,
That'd be
as soon
cool.
as I get it.
Okay, that'd be great. Yeah. All these visuals are really great. Okay, so back to questions. And I had lost the capability of any kind of control on the Zoom, so I had I don't know. So I'd lost it there for a while. Okay, so we're talking about Southern New Hampshire. We need some people to get some names for people that install there. That again, I think we best deal with on our website as a resource, which we will address. The Meeting House wants to compete with St. Patrick's Cathedral, it looks like, which is cool. And this is a great question. All right, so Steve Berry writes, we want to get the Meeting House, which is where we're supposed to be this morning, as far off the grid as possible, but for old buildings, it seems cost prohibitive unless we get large grants. Do any of the companies work with help being an entire village get off the grid because the Meeting House and the Sheldon store could set the standard for a village by working on a system that we could seek grants for because we are both 501c3s. So I guess that's more like a district loop or a pairing of buildings, which is an interesting different technology, or not different, but expansion on what we do here. Which, would somebody like to address that? I could attempt, but I think I'm not the expert here. So
My guess is they would probably, unless the buildings were right next to each other, which I don't know if they are or not, but generally speaking, you would want to do individual ground loops for them. It is a tough challenge what they're proposing, because a good part of the incentives come from the fact that you get federal tax rebates. That is planning on changing. If this new bill gets passed, it's going to be I don't know exactly how it'll work out. Kevin, you may know better, but it sounds like they're just going to send you a check or something to that effect as a form of the rebate.
So they're moving it or getting us parity. You know, geothermal will have parity with solar in section 48 of the commercial tax code. So it'll be a 30% tax credit, which is great if you have something to offset that against historically. But one of the changes in the Build Back Better bill, which is a mouthful, is they're attempting to make this refundable. So for LMI populations, for disadvantaged communities, for 501c3s, you would get a check back to offset the cost. And typically the 30% is there to offset a majority of the ground loop and a significant portion of the heat pump side of things. And if you can reduce the cost on those two key components, then the cost to do a geothermal system should not be any more expensive than upgrading a conventional system, which is the ultimate goal. You know, people don't do this because they perceive it's too expensive. And it is expensive up front, but over time, it reduces costs. It changes operating budgets over a long period of time. It makes it a lot easier to operate historical facilities. Is there anybody working?
Can I
Yeah, go
share
ahead.
a personal story? My husband and I renovated an 1852 general store. It was 4,000 square feet. It had been in a fire, so it had a lot of water damage. So we basically had an opportunity to gut it, and we re-insulated it properly. We put in 2 geothermal boreholes, and we heat and cool the store and 2 apartments for $90. We sold it since then, but $90 a month was the cost for the operation of all the heating and cooling for the store, which, had a lot of refrigeration and, cooking surfaces and such. So, it was a wonderful application. Then, since it was a business, there's something called depreciation, and this is not my field, so correct me, but over 5 years, we could depreciate the investment, which I believe it actually came out to paying for the geothermal system, which I believe was about $85,000, but it paid 110% of that $85,000. So as far as investment wise, why would we put in any other system? It was fantastic. Now we got a wonderful, beautiful, low cost system for the life of the building. So a lot of little nuances there that people might not be aware of.
And I assume that when you did that, you had a contractor that worked with you, as opposed to, sometimes when you get into bigger projects, there's engineering fees and redundancies and added expenses that go into the design of some of these larger projects out there. And those can actually price systems right out of the budget.
I think you're right. But we did see the long-term benefits, so we went for it, and it did pay for itself. So that was a good investment on our part, we felt.
No, and we always look at, as part of that, upgrade investment, whether you're talking new construction or remodel or just a general replacement, you might spend $25,000 or so after all the incentives to do this, but there's cost avoidance that you're not putting in a new furnace or air conditioner or boiler with mini splits or some other combination like that. So the incremental cost is really what we look at more than anything else. In new construction, it's typically very, very minor. 4 or 5,000 on the low end, 8,000 on the high end for a new system, but they definitely pay for themselves.
The good thing too is everybody's educating themselves now as to their options. So if your boiler breaks down, people just say, just slap in a new old thing because I don't have time to figure this out. But by educating yourself now and being prepared for the future and planning, you can, when you do switch it out the next time around, your boiler or your whatever, you're going to be putting a new non-fossil fuel boiler, or not boiler, but mechanism.
That's one thing that has changed. We have historically, it's been kind of a cause and effect with ordering equipment and installing a system. Now we stock equipment, and a lot of dealers do, a lot of installers do. So if your forced air furnace goes down, you can very easily have your contractor come in and install the geothermal system. And typically within a day, you can be up and running on electric resistance until the borehole gets in.
Kevin, that's you. But if you go to some of these big contractors, at least in my area, they don't know that. And they just slap, your first call is the person who put it in, and they just put in what they put in before. Right. But education is the key to change. And we do need to reach those people who are installing the same old to upgrade to new technologies. And that's a whole nother venue. It
is. Slowly we're getting there. It's more about there are options. We have some systems are capable of connecting to an outdoor air source coil temporarily. Mm-hmm. And then you can transition to closed loop after the fact. So it's that emergency piece is becoming something that industry is slowly able to tackle.
Mm-hmm. I did want to bring up that our future workshops will also help you prepare for this transition to clean heating and cooling by making your home more efficient and possibly adding solar, because that's a great way to run these things, and to, so look at future workshops that you can always do something. Don't do nothing, do something. I did want to mention too that the news is that I guess 36% increase in heating fuel prices for this winter. I mean, anything you do for energy efficiency, you might break even by the end of the winter, but it's really going to hit people. And this is when we're going to see a big rush when it hits the pocketbook as to, I got to do something about this. And this is the solution.
Right.
Start now.
So there has been a few people that have been commenting and looking for contractors. I see Colleen was looking for one in Cape Ann, Bob in Southern New Hampshire. If anybody is watching this and is just thrilled about the technology, but starting to do a little research on the contractors, don't be afraid to reach out to me. And the reason why is, so we are still a fairly small heat pump manufacturer. We are looking to grow the base of contractors that we work with. And we want to only really select contractors that are going to represent our product well. So we are actually also in the search for high quality geothermal contractors. And we have, I think, being a former contractor ourselves, we have all the skills that we need to properly assess, if someone's going to be a good candidate or not. So we'd be happy to work with anyone out there in the New England area who's looking to convert. So don't be afraid to give us a message on that. I'm definitely willing to help you with it.
We have a question about when are air source heat pumps better than ground source and vice versa. So I want to give this a fair view, because there's pros and cons to each one. And we do have a kind of heavily weighted ground source group here, but that doesn't mean that there aren't applications. And this is really for our international person, because in the UK, and I do watch Fully Charged from the UK every week, they are definitely pushing air source heat pumps. And one of the cons is that, well, first off, the pro is the expense is less. The con would be it doesn't last as long. It also uses more electricity, which everyone's concerned about overpowering the grid. I have an opinion about that. I will not share it probably because I don't want to start controversy. But this isn't the forum for that. But that is one of the cons, I guess they're saying, is that it would overload the grid during peak demand. So I don't know, Kevin, you do install these, so I think you probably have best knowledge about air source heat pumps versus ground source. Your own home was a perfect example of when it would be more appropriate to put in an air source.
It's a funny topic of conversation. The best time, in my opinion, is when you can't do a ground source. And ultimately, I'd rather have a heat pump in a building than a fossil fuel system in a building. Cost is always a piece of it. There's short-term immediate costs, there's long-term operational costs, there's life cycle costs. They don't last as long. But at the end of the day, it's getting the gas meter or the propane tank or the fuel oil tank out of the house. Because once that's done, that property is set on the electrification path. There's a lot of ways that you can deal with the solar piece to offset some of the electric consumption, the peaking with batteries. I mean, there's a lot of ways to approach this. There is no right or wrong answer to that, and spoken by a ground source guy. If we can put a loop in, it's always going to be better, my opinion, to put a ground source heat pump system in. If you can't get a ground loop in, go air source and couple other technologies with it. Put a battery wall in. Buy a Tesla. At some point, they'll be your battery. Who knows? So there's no situation where you shouldn't have a heat pump in this day and age. It works in any climate, any home, any situation, anywhere.
And it's really where you get your information from is really important because people are very opinionated about this.
Mhm.
So yeah, please. That's why I highly recommended the membership to New York Geo or to Solar Fest or organizations that have vetted and are credible and that, you know, don't expound fake news. Let's just say.
I used to be against them.
Air source.
Yep. And then we put them in, and they work just fine.
Well, I will share. Since this is Solar Fest, I referenced Dr. Richard Perez from SUNY Albany, who is a meteorologist and has a theory of overbuild and curtailment for solar. And he doesn't feel, he has done research and data and backed up his information with that we do not have to worry about the grid with air source heat pumps. We can build out the grid with renewables in order to accommodate that and accommodate all peak times. So I won't go into it further, but you can check out Dr. Perez's work, and I can have Mike put that on our website so that you can see his 26-minute video, which explains it beautifully in English language, not highfalutin stuff you don't understand. Okay, let me look at this chat. I hope we answered our UK question. Okay. I don't know if there's any other questions from the audience. I'm just going to look here and see what else I've put down, just kind of coming to mind as we were talking. Oh, I think one other thing, which is probably, I think very important, is that we did speak about a bill that are being reviewed right now. Any support you can lend it would be wonderful. If this isn't passed, it's really going to set us back. We need to reach parity with solar. So maybe we can put a link in of those bill numbers and who to contact and make it easy for you to do that. If you are willing to do that, that'd be appreciated. Kevin, you mentioned something about a standardized system. I'm not sure I understood that. If you could explain that briefly.
So what we did is we standardized ground loop configuration because, you know, we've gone with, like Rob mentioned, larger diameter pipe, higher thermal conductivity grout, and standard loop design to minimize flow rates, pumping watts. And we've done the same thing with the horizontal systems, how many circuits we put in, the size of our header pipes, everything we can do to minimize pressure drop through the ground loop. Inside the building, you know, historically, you could go into 10 different homes from 10 different contractors and see 10 different methodologies of installation. And you see it a lot more with hydronic systems than you do with forced air systems, although I've seen some doozies. But the ultimate goal was to have a repeatable, scalable installation process that it looks identical from home to home to home to home. And anybody from any one of the companies could go in and service it. They could go in and diagnose an issue. They could go in and repair anything. And it set everybody on a path of being able to offer a standardized price as well, which was a key component of what we were going for. So kind of to what I was saying before, the cost difference between a 3-ton or a 4-ton, it really doesn't vary an awful lot because it's that first cost of buying the heat pump and getting into the house. And that was how we designed our program. You know, under the old NYSERDA program, it was a pretty much a guaranteed under $20,000, you could put in a forced air heating and cooling system with 100% domestic hot water. Changes in the rebates and the programs and the tax credits over the last 2 years has probably bumped that up to that 24, 25,000 range. But the variable speed technology of the heat pumps allows us to adapt to duct systems. It allows us to make minor changes. They might seem major, but to us they're minor, of increasing some of the ductwork sizes, return air capacity, running something to the second floor, because there's a lot of homes that don't have return air on the second floor. And then it's just repeatable. And what that does.
Can you explain variable speed? I'm not sure everybody knows. I think they do, but I'm not going to assume that.
The compressor is variable speed. I call it load matching.
Okay.
So as the home heating or cooling load goes up or down, depending on the time of year, you can look at bin charts and weather data and how that all plays in. But the heat pump basically matches the home's losses in the winter and gains in the summer. So it's just constantly replacing BTUs or removing BTUs to maintain an even, comfortable temperature.
Can I contrast that with like a gas boiler that the thermostat says, I need heat, it blasts it out. And I don't need heat, it stops. And then there's that period when it starts feeling a little chilly and it blasts it out. This is variable. It just maintains constant and comfort.
It's cruise control versus stop and go is how we look at it.
So yeah, I just wanted to bring that up because I think that's a real benefit for heat pumps as opposed to our conventional systems.
Well, and you said it just right. It's heat pump. So it's, you know, every cold climate air source heat pump at this point is a variable capacity system. And with the 7 series by Water Furnace, I believe Climate Master has a variable capacity unit as well. New York State's very heavily dominated by Water Furnace, but it reduces the energy usage in a home dramatically. We've seen about 35% energy reduction, even in a swap out from a 2-stage to a variable speed system.
How much?
35% year over. You know, if you take out a 6-ton compressor that's got a massive current draw and impact every time it fires up versus the steady pull of variable speed, it's a big energy savings.
So this would be like being at a stop sign and hitting the gas. You're gas guzzling. And then you hit the brakes and you just stop. Or you hit. That's the way that a non-variable speed uses energy, but a variable speed is that consistency. And it's like traffic circles versus stoplights. You save energy by just flowing around it as opposed to stop, go, because there's energy required to do both of those processes. Hope that helps.
So energy saving is one piece of that. It's a big piece. The wear and tear on the equipment is also a big life cycle savings. When something kicks on and kicks off, it wears stuff out.
Same with electric cars. So that's a good analogy. And then no one's really mentioned health benefits. We've mentioned comfort, cost, long-term cost in particular, health benefits. There's no combustion. So there's no, and safety, security. There's so many different benefits that I see. You know, my husband does have asthma, so we had to go. Oh, another thing in my house, I'll just share this. I don't open my windows, which is like, I'm an outdoor girl. How can I not open my windows? Well, I have a heat recovery ventilator, which brings in fresh air every 20 minutes and it turns over the air in my home, and it's filtered. So I don't get the pollen, I don't get the dust. It's nice and clean. It even has a MERV 13, so that it can filter out the viruses. So the environment that we're living in is actually healthier than if we just let all the pollutants in from outdoors, with the windows, and we have a controlled, comfortable year-round temperature. And if I want to go outside, or if I want to open my doors, I still can, but it is very comfortable. So I just want to throw that out there because that might be of concern to some of the people attending. All right, so I see if there's anything else in the chat. I don't know if we have any other questions. Okay, I think we are good with the questions and they're not coming in. So I got a feeling that things are slowing down. So maybe it's a good time to kind of like sign off and thank everybody and remind you that we do have upcoming workshops. I do want to thank our speakers for their time and energy and talent and knowledge. It was excellent. I really do appreciate your time, gentlemen. And
Thank you.
Happy to do
Thank
it.
you.
yeah, if
Thank you.
anybody else has something else to say, you know, feel free to speak your piece now, or I guess we can sign off for the day. And we
Don't
hope you-
hesitate, like Matt said, reaching out with questions, you know, even if we're not in your area. You know, again, as a board member for New York Geo, we know somebody. We can
Right.
find somebody for you.
Exactly.
So,
Yep, we're here to help.
very good. Thank you.
All right, thank you, everybody.
Thank you.
Thanks.
Take care.